Hi, good morning. Today in our lecture series, we are going to discuss about the test requirement and metrics of VLSI testability and design for testability. So, in this, as this is the first session, we shall discuss about the introduction. Before getting into the VLSI testing on the VLSI testable methodologies, let us see what is VLSI and what are the important parameters or associated with the VLSI technique. So, before getting into the VLSI, first we must know what is IC. That is, IC is nothing but of a integrated circuits. By the name itself, you can understand. So that the circuit has so many things, so many components integrated with each other in in a specific layout. That is called an integrated circuit. So these integrated circuits have grown in size and complexity since the late 1950s. So there are several generations of there from small scale integration to a very large scale integration. So those are SSI, MSI, LSI, VLSI. So the VLSI is very familiar and very popular. So many developments were took place in this VLSI. So here, according to Moore's law, so Morse is a scientist. He stated one law that means the scale of ICs doubles every 18 months. So the scaling means if, for example, every 18 months the number of transistors in this IC that will be doubled. That is called that is the statement given by the Morse. So growing size and complexity poses many and new testing challenges. As the number of transistors are increasing, what happens? Many challenges, right? Many challenges are like the predominant challenges are the layout and the power consumption. So that challenges are emerging. So that need to be rectified. So that is to first we to rectify the challenges we have to know what kind of the problem exists in the IC. So to find out the problem, we need a testing methodologies, appropriate testing methodologies. Corresponding graphical representation for year-wise, the number of transistors count is given in this diagram. And the importance of testing, the most are results from decreasing feature size, that is dimension, from 10s of micrometer to 10s of nanometer for transistors and integrating wires. Operating frequencies have increased from 100 kilohertz to several gigahertz. So decreasing the feature size, increasing probability of defects during manufacturing process. So rule of 10, that is cost to defect fault IC increases by an order of magnitude as we move from device PCB system field operation. So testing performed at all of these levels. So testing also used during manufacturing to improve yield, that is failure mode analysis, FMA, field operation to ensure fault-free system operation, initiate repairs when faults are detected. So testing typically consists of applying sets of test stimuli to input of circuit under test, that is CUT, and analyzing output responses. If incorrect, fail, CUT assumed to be faulty. If correct, pass, CUT assumed to be fault free. Input test stimuli given to test under test, that is CUT, then output response analysis. So the testing during VLSI's life cycle is given over here. So this is the flow diagram where each stage have different category of testing. So for example, first it starts from design specification, then design, fabrication, packaging, quality assurance, design verification, wafer test, package test, and final test. So different levels of abstraction during design and simulation used at various levels to test for design errors in behavior or RTL, design meeting system timing requirements after synthesis. So yield and reject rate. That means yield is nothing but of number of acceptable parts by total number of parts fabricated. And reject rate is called number of faulty parts passing final test by number of parts passing final test. So these are the two important parameters where VLSI testing is to be performed. In electronic system manufacturing, there are several concepts are there. So like from starting with PCB fabrication, so bare board test is taken place in this level, and the PCB assembly board test is taken place, and then unit assembly, unit test will take place. Then system assembly, system test will be taken. So when we are comparing this overview of VLSI testing technology, there are ATPG, that is automatic test pattern generation, then fault simulation is there, and design for testability, that is DFT, and three basic approaches are adopt techniques, scan design, built-in self-test, that's BAST. So design for testability, the controllable test point is there, and observable test point we are analyzing, and the scan design and good CAD tool support is given over here. And boundary scan design applied to IO buffer of chip used for testing interconnect on PCB provides access to internal DFT capabilities. IEEE standard 4-wire test access port TAP. So built-in self-test, that is incorporate test pattern generator, that is TPG, and output response analyzer ORA internal to design. Chip can test itself, can be used to at all levels of testing. Thank you.